Okay, section 1.2. This is the very first section we'll start with in this class. Functions and graphs. We're just going to look at some functions and their graphs that you've seen in the past, kind of remind you of which ones we really need to be familiar with going forward in this class. And first of all, we'll go through some things that some of my past students have had to say to give you a little bit of idea of what we're heading into in this class. So calculus is one of those courses that takes into account a whole bunch of information and puts it all together. One nice thing about this class is that it all comes together. It's not a bunch of disjoint things. Calculus is all one sort of continuous subject. Everything we use right at the beginning, we're going to use at the end. So because of that, like Cassie says here, it really connects in the end. So even if you're having some trouble early on with one little piece, just stick with it and you might find that a month or a week or however long, it's all going to come together. So you just have to persevere with that. This is a recurring theme. You're going to see from some of the past students' advice to do your homework. And along with doing your homework, ask questions. You really need to make sure that you don't allow yourself to just accept that you can't do a problem. If there's something you don't know how to do, please reach out to your friends. Please reach out to me. All of those resources you have online to really try to make sense of the material. Don't let anything get past you without really making sense of it. And like I said, and like Caitlin says here, I am more than willing to help you out with any questions you have. I love answering your questions, whether it's in class, before school, after school. Please make sure to use me as a resource. I would love to help. And along with doing your homework, make sure you do it the night it's assigned. Do it first thing because we're going to build off it the next day. If you don't do it, you're not getting that practice that you need. So make sure you keep up with it day after day. Here from Robert, he would ask questions, and that I think I've already mentioned once before that asking questions is huge. It's real easy to just keep your head down and not ask a question if you have one, but if you have a question, guaranteed other people have the same question as well, so please ask. I think you're starting to see some common themes here, doing your homework on time once again. And this is probably good advice for life. Drink lots of water, hydration is key. Eric here has some advice for us on good go-to topics if you want to get me off task, so feel free to give those a shot whenever you like. And it never hurts to bribe me with an iced vanilla latte. All right, so now we'll go ahead and get started with some actual math. This is actually a pretty good list right here of some of the graphs that you should know for this class just off the top of your head. So we've got sine, cosine, tangent, cotangent, absolute value, polynomials, circles, 1 over x, square roots, and then the last one there. Okay, so here are the ones that you really need to know. Linear graphs, y equals mx plus b. You guys remember that from years and years ago. You've used that a whole bunch. You'll find that we actually use the point slope form a lot in this class. Y minus y1 equals m times x minus x1. So if you recall, that's if you know the slope of a line, if you know a point on the line, you can plug those in for m and x1, y1, and that will give you the equation of the line. So y equals 3x minus 2 has a slope of 3, a y-intercept of negative 2, so you can see it crosses the y-axis at negative 2, then it goes up 3 and it's an over 1. Y equals x squared, that's a parabola centered right at 0, 0. Y equals x cubed. This is cubic, and so it starts going down to the left, ends going up to the right. Absolute value, so all of the outputs are positive. 1 over x, you can see that there's a vertical asymptote at x equals 0. Okay, y equals e to the power of x, so this is exponential. Recall that e is the number 2.71828, on and on. It's an irrational number, just like pi, and we'll see really throughout this class that that the base e has some really special properties. So of all the exponential functions, e to the x is the most important for us. Natural log of x, this is the inverse of e to the power of x. If you remember, inverses are essentially flipped across the line y equals x. So if you imagine there's a mirror at y equals x, it gets rotated around. So think back to e to the x, imagine the line y equals x, and e to the x would be rotated around that line, creating natural log of x, because they're inverses. Sine of x. Sine of x goes through the point 0, 0, and creates the sinusoidal wave. Cosine of x goes through the point 0, 1. Tangent of x. And tangent of x has all these vertical asymptotes. And if you remember that tangent is equal to sine over cosine, so anytime cosine is equal to 0, that's when we end up with one of those vertical asymptotes, because we can't divide by 0. Okay, so just keep in mind throughout all this that we're going back, we're reviewing everything that you need for this class, and a lot of what you did last year was really good stuff, but you really kind of go above and beyond there to get a good, strong foundation. In this class, you don't need to have quite the depth of knowledge you had last year. We will deal with, some of those more base functions. We're not going to deal so much with translating them all around or moving them up, down, stretching them, all that sort of stuff. So as we do need things from your previous classes, we'll try to do some brief review of those. Okay, some review of some terminology, domain and range. What we typically think of is domain is the input, range is the output. So you have your independent variable, x, sometimes we use t, dependent is y. So domain is the set of all possible inputs, which is the x values. Range is the set of all possible outputs, that's the y values. Now, sometimes a function will have a natural domain. So y equals the square root of x. We know we can't take the square root of a negative. So our domain would be all values of x from 0 to infinity. And that's just because of the function that specifies that the negatives don't work. We can also restrict the domain if we want to. I could say I have y equals square root of x, but I only want to look at x values from 0 to 2. So I could specify that my domain for a particular function is going to be some smaller range of values. Okay, so we want to find the domain and range of 1 over x. And when you're thinking of domain, it's often easiest to think of, instead of what can you plug in, what can't you plug in? Well, we can't plug in x equals 0 because we can't divide by 0. So our domain is all values of x such that x does not equal 0. That's set builder notation. Typically, you would end up just writing x does not equal 0. That'd be fine. You could write this another way, negative infinity to 0, union 0 to infinity. That's interval notation. Notice that we use open intervals on the zeros to indicate that the 0 is not included. If we graph this, we can now really clearly see our range. Range is often a little bit more difficult to come up with without looking at the graph, although it can be done. We can see that the y values never become 0, so the range goes from y equals negative infinity to 0, union with 0 to infinity. All right, so if we want to find the domain and range of y equals root x, first looking at the domain, we know that we can't take the square root of a negative, so x goes from 0 to infinity. Notice we use a bracket on the 0 to indicate that the 0 can be included. Now, before I even show you the graph of root x, this is one that we should know. The way I kind of think of this, we know y equals x squared, that's a parabola. Root x is the inverse. But recall that it has to be a function, so we only take the top half. So it kind of looks like a parabola turned on its side, and we can see there that the range goes from 0 to infinity. Okay, we can talk about different types of symmetry. So y-axis symmetry means symmetric about the y-axis. If you imagine there was a mirror on the y-axis, it would just reflect over. And we also call this an even function. If you have and what that comes from is if you have a polynomial with all even exponents, it's always going to be symmetric about the y-axis, because when you raise a number to an even power, it's always positive. So it doesn't matter if you plugged in a positive x or a negative x, they'll all be treated as the positive. And there's another even polynomial. Absolute value of x, another even function. Cosine of x, another even function. And the general rule is if f of x equals f of negative x, for all values of x, then the function's even. So if you look at that cosine function, if I plug in x equals 5, I get y equals, looks like something like 0.3. And if I plugged in x equals negative 5, I get the exact same y value. So I plugged 5 and negative 5 into the function. They both gave me the same output. If that happens for all values of x, then the function's even. Okay, if you have a polynomial with all odd exponents that has origin symmetry. Origin symmetry, you kind of think of it in two steps. If you rotate around the x-axis and then the y-axis, everything will match up. So it's kind of a two-step process. So you can see if I plug in x equals 2, I get an output of 4. If I plug in negative 2, I get an output. We call this an odd function. Sine of x is an odd function. And the way we can determine mathematically if a function is odd, f of negative x equals negative f of x. So for example, if I plugged in x equals 3, I can see I get something like 0.1. If I plug in negative 3, I get negative 0.1. So it's going to be the same value, but negative. If something has x-axis symmetry, it doesn't pass the vertical line test, and it's not a function at all. So x equals absolute value of y, not a function. Okay, piecewise functions. These are something that we will encounter a lot in this class. We want to make sure we're kind of comfortable with how a piecewise function works. The big idea with a piecewise function is we describe the function in pieces. So we can say from x is negative infinity to 0, it behaves this certain way, and then from 0 to 2, it behaves some other way. We can break it up into different sections of the domain. So here we have f of x is equal to negative x when x is less than 0. So for all values of x less than 0, we'll have the line y equals negative x. And then between 0 and 1, it will behave like y equals x squared. And when x is greater than 1, it will behave like y equals 1. So let's see what that looks like. Negative x. That's a line that goes to the origin and goes down 1 over 1. But then we stop right there at x equals 0, and I use an open circle on the graph to indicate that that point is not included. And then we graph y equals x squared, which is our parabola, but we only graph it from 0 to 1. So we just get that little section of it right there. Notice that the 0 is included and the 1 is included, so I put a dot at each end to indicate that that point gets included in the graph. And then we have y equals 1 for x greater than 1. And that's a horizontal line, goes straight out to the right. So we can describe some graph like this that, is comprised of all these different pieces by using a piecewise function. Okay, let's go backwards with this one. We have this graph. Let's see if we can figure out how to describe this in function notation. So look at the first line there. Goes through the origin, goes over 1, up 1. So that's the line y equals x. And we have y equals x from x equals 0 to x equals 1, not including the 1. And if we look at this other one, we could use the point slope equation, y minus y1 equals m times x minus x1. Or probably what you do most often is to just realize that this has a slope of 1 and it has an intercept of negative 1. And we know that the intercept is negative 1 just by kind of imagining what would happen if we extended that line down. So that becomes y equals x minus 1. So our piecewise function, y equals x from 0 to 1, including the 0, not including the 1, and y equals x minus 1 from 1 to 2, including the 1 and including the 2.